Welcome back. This is Mr. Hyper, and today I'm taking you through Euler propagation. And before I take you to Euler propagation, allow me first note some terms here which we normally or which we commonly use. Here, we've got a term called absolute Euler. Absolute Euler. When we say absolute Euler, right? If we have a correct number x, if we suppose to have a correct number x, and then small x as its approximation, we have correct number and then its approximation, then its absolute Euler, or the absolute Euler in this x is going to be denoted as px, and will be given by the magnitude of correct number minus the approximate. So this is how we get absolute Euler. Then we've got what we call relative Euler. Relative Euler is given by, and denoted by RE. It's given by the magnitude of absolute Euler out of the number, or one can say relative Euler is equals to absolute Euler magnitude over small x. But this delta x, but delta x is the magnitude of x minus small x, implying that then the relative Euler will be x minus x out of capital X. Okay, so if we work on that, this can be the same as this over this minus this over this, which can be 1 because it will be x over capital X, which is 1, then minus small x over capital X. So that is what we call the relative Euler. Then if we say percentage Euler, we have a term called percentage Euler. Percentage Euler, you get the relative Euler multiplied by 100. That one will always give you the percentage Euler. Okay, now looking at all this, it can now move us to Euler propagation. When we say propagate, when we say Euler propagation, it means that we want to see the operations of addition, subtraction, and the division and multiplication, how we treat their Eulers. Let's begin with the Euler in addition, and we propagate it and say Euler in addition. If we say Euler in addition, we are going to consider values x and y. We consider values x and y. For all cases, we are going to consider these. And we are going to assume that these values are approximated by x and y, small letters. Okay, so now to get means that the Euler in x, since we are looking at Euler in addition, it means that we let our z to be equaling to capital X plus capital Y. Okay, but if we let that to be equaling to that, then our capital X is going to be equaling to the approximation of x plus small change in x, and our y is going to be equaling to approximation in y plus change in y. Approximation in z is going to be equal to, actually our z is going to be approximation in z, small z, plus change in z. And I want you to know that the small z will be going to small x plus small y. Now, if we have all this, then now we substitute. It would mean that to get this z, we shall have small z plus delta z equaling to x will be small x plus delta x, then plus smaller y plus delta y. That's what we are having. So implying that our delta z is going to be equaling to x plus delta x plus y plus delta y minus z. We shall bring z this side, which z is x plus y. Looking at this, it will be our delta z is equals to x plus delta x plus y plus delta y minus x minus y. After opening the brackets here, x and minus x will go, y minus y will go. So we shall have our delta z as delta x plus delta y. All right, so if we take the magnitude either sides, which is going to be our delta z magnitude is going to be equaling to magnitude of delta x plus delta y. All right, implying that our delta z here is going to be equal to, if we introduce in what we call the triangular inequality, so it is going to be less or equal to, we separate them, delta x plus delta y. When introducing the triangular inequality, you'll split them. Now, this is the absolute error. The absolute error is given by the sum of the individual absolute errors. So that is what we are having. Sum of individual absolute errors is what we are having. Now, continuing, if we continue to see what will happen for that case, that is the absolute error. Then we need the relative error. So the relative error, the relative error is going to be equal to, we say that it is delta z over z. So it is going to be delta z is a delta x plus delta y over z, which is x plus y. As simple as that. So that is how we propagate the error in addition. So let's look at the error in subtraction. Error in subtraction. So we are going to consider the same values, only that z this time will be equaling to x minus y. Okay. Remember, we had said that our small z will be x minus y, and our x is going to be equaling to small x plus the change in x. And our y will be equaling to y plus change in y. So substituting there, you'll have your z plus delta z is equals to x, which will be x plus delta x, minus y, which is y plus delta y. So it would mean that our delta Z is going to be equaling to X plus delta X minus Y minus delta Y, then minus X minus Y. So this will be delta Z is equals to X plus delta X minus Y minus delta Y minus X plus Y. So this one will reduce to delta Z is equals to delta X minus delta Y. All right, so if you take the magnitude to be delta Z here is equals to the magnitude, it will be delta X plus negative delta Y. But if you take the triangular inequality, it will be delta Z is less or equal to, we separate delta X plus the magnitude of negative delta Y will be delta Y. So still the maximum possible error still is the sum. In the sum or difference of two quantities is the sum of absolute errors. You can see that they are the same. So the same applies to the relative error. The relative error is going to be equal to, we shall divide the absolute by the original, which is X minus Y. So it is going to be delta X plus delta Y divided by the original, which is X minus Y. And this one can split it further and say delta X over X minus Y plus delta Y over X minus Y. So this is okay. This is okay. So of course questions are going to be done. We are going to see. Let me first put in some example maybe here, and we see. In case they say given as 1.652 and maybe B as 9.78, and they say find maximum error, find maximum error in Roman 1, A plus B, and Roman 2, A minus B. So if you look at this, if we need the error in A plus B, error in A plus B is going to be, since it is, we say that the maximum error in addition is the same. So sum of individual errors. So it will be error in A, error in B. So it just error in A is 0.0005. Then the one in B is 0.005. You count the number of decimal places, then you add a 5. So it would be 0.0055. In A minus B, still the same because they are the same. We propagate them the same way. So error in A minus B still is going to be equaling to error in A plus the one in B, since we've seen that they are the same. So still the same thing and the same working. What if they say find the values of A of 3A minus 6B plus 9C if A, B, and C are used to approximate B and C respectively, and that A is 3.456, B is equals to 2.67, and C is 1.6784. We need absolute error. We need absolute error. Find the values of this. So we need absolute error. So in other words, this 3A minus 6B plus 9C would be the same as 3A plus 6 negative B, then plus 9C, which is the same as 3A would be approximated by delta A plus 6. Since it is absolute, shall take negative, or we shall take it as positive, then plus 9 delta C. Then you do the necessary 3 into delta A. A is 3.456. These are 3 decimal places, so we shall have 1, 2, 3, and 5 plus 6. B is 2 decimal places, so we shall have 0.005. Then C, 9 into 1, 2, 3, 4. So 1, 2, 3, 4, then 5. So this one will give you the value, which is 0.03195. So can get the value here, add value here, add value here, and get that. So let's look at the error in multiplication. After that, we do general examples and we see. Error in multiplication. So still, if we have x, y, x and y as our numbers, it means that our z will be equaling to x, y. If our z is equaling to x, y, then our small z is going to be equaling to small x, small y. And we know that our z is equals to small z plus a change in z. And our y is small y plus change in y. And our x is small x plus change in small x. Now, looking at all this, it would mean that our z, we are going to substitute into this. Our z, which is z plus small z, so it will be z plus delta z is equal to x, which is x plus delta x times y plus delta y. So we are going to expand. This is xy plus x delta y plus y delta x, then plus delta x delta y. All right, so this is our z plus delta z. So it means that our delta z alone is going to be equal to xy plus x delta y plus y delta x plus delta x delta y minus z, which is xy. These ones will cancel. So we shall have our delta Z as X delta Y plus Y delta X plus delta X delta Y. So what we do here, we shall neglect delta X delta Y because it is very small. So you neglect delta X delta Y for it is small. So implying that what we shall have will be our delta Z is equaling to X delta Y plus Y delta X. When you take the magnitude, delta Z is equal to X delta Y plus Y delta X. If you take the triangular inequality, it will be delta Z is less or equal to, these are equal signs. So here we bring in the triangular inequality. The triangular inequality will move X outside, then delta Y in the magnitude must be deltas, then plus Y delta X. So that is what we are having as absolute error. Implying that if we need a relative error, will be delta Z out of Z, which will be X delta Y over XY, because we say that you can divide by the small or the bigger. So Y delta X over XY, implying that the magnitude of delta Z over Z is the same as the magnitude of X will cancel, so we shall have delta Y over Y plus Y will go, we shall have delta X over X. When you bring in the triangular inequality also in this, delta Z over Z will be equaling to, will be less or equal to, if you bring in a triangular inequality, we shall have delta Y over Y plus magnitude of delta X out of X. So this is what we would have as the error in multiplication. Let's propagate in division, and we have general examples. Error in division, those formulas are examined, proving them are very much examined. Error in division. So if we still have our Z, I'm going to consider now X over Y. It would mean that like a small z will be equaling to small x over small y. But remember, small z is equals to, actually our z is equals to small z plus delta z, and our y is equals to small y plus delta y, while our x is equals to small x plus delta x. Implying that if we need this z, which is it would imply that z plus delta z is equals to x plus delta x over y plus delta y. You can use two ways to do this, and you can use two methods, as I've told you. One can use binomial theorem, another person can rationalize. Now what we do is going to be equal to, remember, z plus delta z. It's going to be equal to x plus delta x, y plus delta y. So what we can do, we can rationalize the denominator, y minus delta y, x, no, up and down, y minus delta y. So we can expand this. This one will come to xy minus x delta y plus y delta x, then minus delta x delta y. Out of, when you work on this down, you have y squared minus delta y squared. Of course, we shall neglect delta x, delta y, and delta y squared because they are too small. And if we neglect them, it means that we shall have our z plus delta z equal to xy minus x delta y plus y delta x out of y squared. So if you have this, so this is going to be the same as z plus delta z is equals to xy. Because we are looking at errors, this is the same as plus x times change in y, which we take positive, so it will be plus x change in y and plus y change in x out of y squared. But we need delta z, so delta z is going to be equal to xy plus x delta y plus y delta x over y squared minus z, which z is the same as x over y. Okay, so we have subtracted a z this side, which is the same as x over y. So here you can take the LCM. If you take the LCM, you're going to have it as xy plus x delta y plus y delta x minus xy out of y squared is our delta z. So xy and xy will go. So we shall be left with our delta z as x delta y plus y delta x out of y squared, right? So you have out of y squared means that our delta z in magnitude is going to be equaling to magnitude of x delta y plus y delta x out of y squared. When you bring in that triangular inequality, it means that delta z is less or equal to, you factorize out x, then delta y plus y delta x everything over y squared. So this is how we get the absolute error. Then let's look at how to get the relative error. Remember, our absolute is delta z less or equal to x plus out of y squared. It would mean that our relative error would be that absolute, which is x delta y plus y delta x. We divide by y squared, then divided by the original, which was x over y. Okay, x over y, something like that. So it is going to be equal to x delta y plus y delta x over y squared times y over x. The y's are going to reduce. So we are going to have our relative error, which is the cos delta z over z, delta z over z. Here it's before the magnitude signs. That is when you have it just plain like that. Then, as we put magnitude, of course, one y is going to be that, so down we have yx. So we shall have x delta y plus y delta x out of xy. Okay. When you put triangular inequality, it is going to be x delta y over y, because it would be over xy, but actually this x is not there, because when you factorize out x, it would be this over this, but x will go with x. So you have delta y over y, then plus even y will go, so you will have delta x over x. Okay, which takes the form of the other of multiplication. So in conclusion, you can see that the maximum relative error in the product or the quotient of any two numbers is the sum of the relative errors of the individual numbers. So addition and subtraction have got the same conclusion, and then multiplication and division have also got the same ending. So that is how we propagate. Otherwise, one can use the binomial theorem, but that one would cost you a lot of time. That one would cost you a lot of time. Okay, but someone may be interested in it. Someone may be interested in that method, division using binomial theorem. So the alternative method, if you have x and y still, we shall say that z plus delta z from where, let me start from some point, x plus delta x over y plus delta y. So this one would imply that our z plus delta z is equal to x plus delta x times y plus delta y to the power -1. Right, so this is the same as z plus delta z equaling to x plus delta x, then times, for the case of this one, we can factorize out y, so it will be y into 1 plus delta y over y, then everything to the power -1. So this is the same as z plus delta z equals to x plus delta x, then y power -1, then into 1 plus delta y over y to the power -1. So we shall use the expansion of the series, where we know that 1 plus x to the power n by binomial theorem is equal to 1 plus nx plus n into n minus 1 x squared over 2 factorial and other terms. But for this case, our n is -1. So it would mean that if we talk about only 1 plus delta y over y to the power -1, this one would be the same as, so for this case, we are going to see that our n is -1 and our x will be delta y over y, because I'm comparing this with this one. Now would mean that just 1 plus delta y over y to the power -1 is going to be equal to 1 plus n, which is -1, into x, so it will be delta y over y, then plus n, which is 1 into, which is negative 1 into n minus 1, that is negative 2, then x squared, that is delta y over y, everything squared, then over 2 factorial. So it would mean that that expansion would give us, of course, we shall neglect this delta y squared because it has high powers. So you're going to find that as a result, you're going to have your 1 plus delta y over y to the power negative 1 as equal to 1 minus delta y over y. We have neglected this being too big, so it has reduced to this. So now it means that our z plus delta z is going to be equal to, we bring here to be x plus delta x, then y power negative 1, then we substitute 1 minus delta y over y, right? So this is going to be x plus delta x, okay? Then this is y power negative 1, which is the same as 1 over y. If you multiply 1 over y here, you'll be left with the 1 over y. Then 1 over y times that, which is going to be minus delta y over y squared. Okay. So this is going to be equal to x over y. Of course, you expand x over y. I multiplied it here, then into that will be minus x delta y over y squared. Then you multiply this one into that to be plus delta x over y. Then this one into that to be minus delta x delta y over y squared. If we neglect this one being too small, it would mean that if you neglect this, because it is very small, so it means that our z plus delta z is going to be x over y minus x delta y over y squared plus delta x over y. But if we need delta z only, we shall subtract x over y. So x over y minus x delta y over y squared plus delta x over y minus z, which z was 1 over x, rather x over y. These ones cancel, x over y will cancel with this x over y, so that we shall be left with our delta z is equals to, we can begin with the delta x over y, then minus x delta y over y squared. So here, since we have our delta z as delta x over y minus x delta y over y squared, it would mean that our delta z into magnitude is going to be equal to magnitude of delta x out of y minus x delta y out of y squared. We are taking the magnitude. So if you take the triangular inequality, delta z is less or equal to delta x over y minus, rather plus x negative delta y over y squared. But remember, this one, you can make it a positive after some conversions. Rather, after taking the magnitude, it becomes a positive. So this will be less or equal to, we can factorize out x over y, so that the whole thing becomes if we put out x over y, here it will become delta x over x, so that when you multiply, it goes back to that. Then plus delta y over y. So that is what we have. Then this one would mean that taking the relative error would be delta z over z, which would be x over y into delta x over x plus delta y over y divided by z, which is x over y, so the reciprocal y over x. X will cancel, y will cancel, so we shall be left with our relative error as delta z over z equaling to delta x over x plus delta y over y. What would this one reduce to? We introducing the magnitude delta z over z is going to be equal to magnitude of delta x over x plus delta y over y, which is, if we bring in a triangular inequality, will be delta x over x plus delta y over y. So that is what we are having. That is what we are really having. And here we can have some great time with questions now, because there are very, very many questions that are always, taking this form. For example, here comes a question. The numbers x and y were estimated with the maximum possible errors of delta x and delta y respectively. Show that the percentage relative error in xy is delta x over x plus delta y over y times 100. So it's a matter of using the propagation methods we've looked at, and you bring an answer up to the end. Just use propagation of the errors, and then you bring the answer up to the end, because there is no big difference here at all. There is no big difference. It's just a matter of looking at the propagation in multiplication. Okay, it's just a matter of multiplication, propagation of errors in the multiplication. Otherwise, the number is very, very, very easy. So by looking at the propagation in multiplication, this number can easily be passed. So it's a matter of moving up to when you get the relative error, and then you multiply it by 100. Okay, so first get the relative error, then multiply it by 100. So I would expect everyone to do this number, and then you see what you would do. Okay. So that is a question to each one of us. Now, since these ones are given as capital letters, you also maintain capital letters. Okay, so one would say, let me give you a hint, but I want every viewer to practice this. You say let Z equals XY. Okay, so it would mean that Z plus delta Z will be equaling to X plus delta X into Y plus delta Y. That is if you want to continue with the capital letters as required. So you continue and you see what you're going to come up with. But it's a very easy question to move on with. Then also another question, all these questions, for those ones who are revising, you must have made these questions in some papers. This one was the numbers X and Y. Let me get this question very clearly. The numbers X and Y are approximated to, okay, with possible errors, delta X and delta Y respectively. Show that the maximum absolute error in the quotient X over Y is given by Y delta X plus X delta Y over Y squared. Okay, so that is what we are expected of proving. Now, the fact that we've proved in the quotient or in a division, it becomes very easy for someone who is doing this question, because it is not any different from the proof that we have made. So in a hint I can give you is that if we let our Z to be equaling to X over Y, it means that Z plus delta Z is going to be equaling to X plus delta X over Y plus delta Y. And then you continue up to when you get the final expression, which I have just proved for you. There are very, very, very many questions. There are very many questions. And there is another one which also can be proven. Actually, let me do all of this for you, then maybe we call it a time. The numbers X and Y are approximated by capital X and capital Y with errors delta X and delta Y respectively. A they want you to show that the maximum relative error in xy is delta x over x plus delta y over y. So that is what is given. And let me see. Then after that, the other part was, after that, the other part was B, if x is equal to 4.95, y is equals to 2.013, are each rounded off to a given number of decimal places. Roman 1, calculate percentage error in xy. Roman 2, limits within which xy is expected to lie. Give you answer in 3 decimal places. So that is the question. Proving is okay because that first part of showing is okay. The fact that we have already seen the propagation in the multiplication. So if we let a small z to be xy, it would mean that our capital Z would be xy. Then to mean that our small x would be x now plus delta x, because they gave us the errors also. But remember, they gave us the approximations now are capital letters. So don't confuse that too. Okay, the approximations are capital letters, while the numbers are small letters. So that's why I say that our small y is going to be equaling to capital Y plus small change in y. Saying that our z plus delta z is going to be equal to x plus delta x, then y plus delta y. You will expand to mean that your delta z alone is going to be equal to, after expanding, you get xy plus x delta y plus y delta x plus delta x delta y minus z, which is xy. So these ones will cancel and remain with your delta z as x delta y plus y delta x. Don't forget to tell me that remember the x delta x is far less than x, and delta y is far less than y. Therefore, delta x delta y reduces to 0 or is approximated to 0. So that is how we get the delta z as x delta y plus y delta x. And then here you can get the relative error. Actually, after reaching here, you can get your relative error, which relative error is delta z over z, which is going to be equal to x plus x delta y plus y delta x, everything we are dividing by xy. So this is going to be equal to, you divide x delta y over xy, it will give you delta y over y plus this one will give you delta x over x, actually over x capital. This is y capital. So that is what you would have. That is what you would have. The whole of it is in one magnitude. Then by bringing in the triangular inequality, that is when you split them as delta x over x plus delta y over y. As simple as that. Then when they say capture the percentage error in xy, you just multiply 100 in this, whereby if you have x as 4.95, then it means that delta x is 0.005. If you have y as 2.013, then delta y is going to be 0.1235. Then you substitute in this, then you multiply by 100. You already have the values of x and y, you know them. So it's just a matter of substituting, then you multiply by 100. You have delta x, you have delta y, you have x, you have y. Okay, so you multiply by 100. The limits, we saw that how we get the limits in our first video. So those are the examples I can do. Maybe in case there is anything you comment, or for those ones, if you get an issue and you want to WhatsApp me, you can WhatsApp 256 75 91 93 260. Wish you all the best. See you.